Continuing on with an annuity is not always putting regular payments away to have a total at the end. Sometimes you want to put a big lump in right now and pay yourself an annuity out of that money over a regular payments over a period of time. It can be a little trickier to get our heads around. So let's just jump in with an example. Suppose you promised your niece an annuity of $300 at the end of each year. It's called an annuity because it's a regular payment. So you're going to give her $300 at the end of each year for the next 10 years. You open an account that pays 7% per annum compounded annually. You deposited enough money today. There's the million-dollar phrase. So that you can withdraw the $300 at the end of each year for the next 10 years. How much money do you need to deposit today? So let's think about that for a minute. The niece herself is going to get $300 a year for 10 years. So the niece herself is going to end up with $3,000. But you shouldn't have to invest that much today in order to pay her that amount. You should be able to invest less because you're going to earn interest on some of it as it sits in that account for a while. Some of it she's going to take very soon and it won't earn much interest, but some of your money will. And we want to know what kind of a lump we put in today so she can take an annuity. These are called present value annuity problems. In this case, I think a diagram might help. So, the question we have is how much money you put in now. So that in 1 year she can take out $300. The year after that she can take out $300 and so on, $300, $300. How much do you have to put in right now so that she can have $300 a year from now? Slightly less than $300. How could we figure that out? So I am just looking at this one right now, kind of off to the side. If I have an amount I want, I'm going to use a compound interest formula. I want to have $300 in a year. How much do I put in right now? I'm going to end up doing a division. So 7% annually, so I don't have to change that number for 1 year. For that first year, I'm going to have 300 divided by 1.07. So for this guy, I need 300 divided by 1.07. To get the next payment of $300, I need just a little bit less because it's going to be sitting in the bank for a little bit longer. So for this one, I need to put in $300 from the same formula above divided by 1.07 squared. For the next one, and so on and so on. For this $300, which is a long time from now, it's got lots of time to accumulate interest, it would be 300 divided by 1.07 to the 9. And there's a whole bunch in between, but the last one would be $300 divided by 1.07 to the power of 10. Will get me that last $300. The amount that I need to put in right now is the sum of all of these divisions. You know that this is a sum of a geometric series, just that this one is a lot uglier. You don't have to write this down. I know on your handout you've got the final answer, the formula that we're looking for, but I just want to show you where it comes from. This is a sum of a geometric series, just like last day. But in this case, our original A value is quite ugly. It's 300 over 1.07 to the 10. And our rate of growth is 1.07, and the n value is 10. We're going to put that into our formula. Again, don't write this down. The sum of all of these divisions would be 300 over 1.07 to the 10. I'm going to add them backwards, in other words. 1.07 to the 10 subtract 1 over r subtract 1, which is 0.07. If I were to do distributive law, I would have 300, 1.07 to the 10 over 1.07 to the 10 minus 300 over 1.07 to the 10. Notice I'm missing him, so I'm going to do all of this, and I'll just tack him on the end. I did that so that these two things can cancel out. And I am left with, taking the 300 back out again, 300 times 1 take away 1 over 1.07 to the 10. There we are. We have our formula. Where the present value is the regular payment either you're paying into it or it's paying out to you, but it's the regular payment. PV is for present value. What do I need to put in there now? I is your rate of gain. It'll change depending on the compounding period. And your number of compound. Here we go. Determine the present value. So this question very nicely told you which formula you want. Present value. Quarterly payments 4 times a year of $350. First payment in 3 months and the last payment in 4.5 years. Interest is 13.4% annually compounded quarterly. Let's see what we know. Our R value is $350. I is 13.4 divided by 4 for quarterly. We will get 0.0335. N is quarterly for 4.5 years, which is 18. We want present value. So we want to know how much do I put in now to be able to take regular payments of $350. 350. Oops, let's write the generic formula right here. Good starting point. R. A little bit different than yesterday's. And do watch that negative sign. Present value is $350. One takeaway. My rate is 0.0335. Decimal 0.0335. All in one step in your calculator, just be careful. You should get $4,674.32. Just an aside, how much interest are you gaining with that little scenario? Well, how much of the money is yours? You're putting $350 in. 4.5 years, every 3 months, you're putting it in 18 times. You're taking out $6,300. You're actually investing 4,674, so you've made some interest. So you took $6,300 from the bank where you only invested 4674.32 yourself, so the interest is $1,625.68. Tatiana is told she can purchase a used Saturn by paying no money down. That's lovely. And making monthly payments of $300. As soon as you see regular payments, you know it's going to be an annuity. Regular payments or payments to you. Then our choice is this an amount problem or a present value? The present value problems that we have done so far is, how much do I put away right now in order to pay myself a certain value? This question here with the car is also a present value problem because she wants a loan. And a loan is money you want right now that you're going to pay off. So generally speaking, if you can keep it in the back of your head that a loan is a present value problem because it's something you want now and you're not saving towards the future. So our present value formula is R1 minus there we are. Let's write in what we know. The present value is the same as the cash value. What loan can she take right now if she's willing to pay off $300 a month? One takeaway, her interest rate is 9.5% per annum compounded monthly. So our I value is 0.095 monthly. Decimal 007916 repeating. It is really wonderful if you can write this in without doing any rounding. You are able to do it that way. Otherwise, your decimal can go right there. We're just trying to avoid errors. It is about money after all. N is the number of compounds, so it is monthly for 5 years. It's going to be 60 over, and this is the same decimal 007916 repeating, or if you and your calculator are friends, we can type it in exactly. The present value will be $14,284.45. That is the loan that Tatiana is able to take. What is the interest she's going to pay on this loan because she didn't pay cash for it? Interest. She paid $300 60 times, $18,000 for a $14,284.45 loan. So her interest, $18,000, subtract what they actually gave her for a loan, $3,715.55 in interest. We'll do the last one by hand and with graphing calculator because they are such a wonderful tool to use. JP wants a Vespa. He decides to take a loan of $23,000 to be paid back over 3 years at 7.5% per annum compounded monthly. We want to know what his payment will be. This is a loan. He wants the money now, to have the Vespa now, and he's going to pay it back. So that is a present value problem. It is an annuity because he's going to pay it back monthly. And we need to go through that thought process with each question. So our formula is silly me. There's only 4 formulas. We do have anchor charts we're going to put up, but you'll have them memorized before you know it. So his loan is the $23,000. We want to know what his regular payment will be. His interest rate is 7.5% compounded monthly. So we need to either write off to the side 7.5% monthly and find that as a decimal, or insert it into the equation exactly as it is. To the negative n, how many payments does he make? 3 years monthly, 36 payments. Over I decimal 0.075 over 12. I fully expect that you are doing all of this, along with me with your calculator to make sure that you're friends. I want to get R by itself. First thing that I'm going to do is get rid of that division on the bottom. I'm going to multiply both sides by decimal 0.075 twelfths. And the next thing I'm going to do to get R by itself is to divide both sides by the nasty square brackets. And the less rounding I do, the more accurate my answer will be. So I've got that divided by this. It will still be rounding. It's still money, so we round to 2 decimal places. 715.44. So JP will have to spend $715.44 every month for 3 years to have his Vespa. But what I'm not sure about is what color he would choose. Let's try this with the graphing calculator because they are such a handy tool to have, and we're going to get it to solve for R. So I've gone to my application button. Number 1 option is finance. The first option there is the TVM solver, and we have information from last time. All right, that's all right. We'll replace it. With an annuity, don't forget that your N value, you have to do the adjustment. So it is monthly for 3 years. If I can't do that calculation in my head, I would do 3 years times monthly, and it can do that for me. My rate is 7.5%, and that I type in as usual, exactly as I see it. The present value is the loan that he wants. It's $23,000, which they're going to hand to him to allow him to have the Vespa. The payment is what I want to figure out in a little bit. Future value, I want to pay that loan off. So I'm going to make my future value 0. So this one is the 36. I need to tell the calculator that. There we are. Payments per year and compound per year match, at least at this point. We are doing it monthly, so both of those are 12s. I'm going to go back and figure out my payment. Remember, it's going to be negative because it's coming out of JP's pocket. So at payment, I'm going to do alpha, enter. alpha, green button, enter, $715.44.